Tonight, we're going to drift into a question that will stretch your imagination beyond anything you've ever contemplated. How big is Andromeda, really? Not just the numbers you might have heard, but the true, almost incomprehensible scale of our nearest galactic neighbor. If you find comfort in these gentle explorations of the cosmos, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious souls like us, who love to ponder the vastness of space. The visuals are here for you, but feel free to close your eyes and let your mind wander through the cosmic dark as we explore together. I'd also love to know where you're listening from tonight. Comment your location below. Picture yourself standing in your backyard on the clearest night you can remember. You look up and maybe, just maybe, you can make out that faint smudge of light in the constellation Andromeda. It's barely visible to the naked eye, appearing as nothing more than a ghostly wisp against the darkness. Most people who notice it at all assume it's just another star, perhaps slightly out of focus. But here's what will absolutely shatter your sense of scale. That tiny, insignificant-looking smudge contains over 1 trillion stars. Let me say that again, because the human mind simply cannot process this number on first hearing. 1 trillion stars. If you tried to count them, spending just 1 second on each star, it would take you over 30,000 years of continuous counting, never stopping to eat or sleep, to count them all. And that's assuming you could somehow perceive each individual star from the impossible distance that separates us. But we're just getting started on this journey into the incomprehensible. Because when we talk about how big Andromeda really is, we're not just talking about the number of stars. We're talking about distances so vast that light itself, traveling at the fastest speed possible in our universe, takes over 2.5 million years to cross the space between us and our galactic neighbor. Think about that for a moment. The light reaching your eyes tonight left Andromeda when our earliest human ancestors were just beginning to walk upright on the plains of Africa. This is where our cosmic journey begins to reveal something profound about the nature of scale itself. We live our daily lives measuring things in feet and miles, maybe kilometers if we're thinking about longer distances. We can wrap our minds around the size of our house, our neighborhood, even our city. Some of us might have a vague sense of how big our country is, or perhaps our continent. But Andromeda exists on a scale so far beyond human experience that we need entirely new ways of thinking just to begin to grasp its true dimensions. The galaxy we call Andromeda stretches across approximately 220,000 light-years of space. To put this in perspective, if you could somehow shrink the entire Milky Way galaxy down to the size of a dinner plate, Andromeda would still be larger than a kitchen table. But even this comparison fails to capture the reality because we're not dealing with flat, two-dimensional objects. We're dealing with three-dimensional structures of almost impossible complexity and depth. Imagine you're an ant crawling across the surface of a basketball. From your ant perspective, that basketball represents an enormous world, curved beyond your ability to perceive, stretching far beyond your tiny horizon. Now imagine that basketball is floating in an ocean, and somewhere across that ocean, barely visible even to the most powerful telescopes an ant could build, there's another basketball. That second basketball is Andromeda, and you're the ant living on the surface of our Milky Way. But this analogy like all analogies when we're dealing with cosmic scales, breaks down almost immediately, because the space between these two galactic basketballs isn't empty water. It's something far more mysterious and profound. It's mostly empty space, yes, but it's empty space that's actively expanding, carrying the galaxies apart at speeds that would make your head spin if you could somehow perceive the motion directly. The Andromeda Galaxy is approaching us at approximately 250,000 miles per hour. This sounds incredibly fast until you realize that at this speed, it will still take over 4 billion years for the two galaxies to collide. 4 billion years. When that collision finally happens, our sun will likely be entering the final phases of its life, swelling into a red giant that may well consume the Earth entirely. Let's pause here and consider what we mean when we say these two galaxies will collide. In science fiction movies, galactic collisions are depicted as violent, destructive events, with stars smashing into each other like billiard balls on a cosmic table. But the reality is far stranger and more beautiful. When Andromeda and the Milky Way finally merge, the vast majority of stars in both galaxies will pass by each other without ever coming close to collision. The distances between individual stars are so enormous that even when two entire galaxies merge, direct stellar collisions are incredibly rare. Instead, what happens is something like a cosmic dance. Gravity pulls and tugs at the spiral arms, distorting them, stretching them, creating new patterns and structures. Some stars get flung out into the darkness between galaxies. Others get pulled toward the center, where the supermassive black holes at the hearts of both galaxies will eventually merge into something even more massive and mysterious. This brings us to another aspect of Andromeda's size that challenges our understanding. At the center of this galaxy sits a black hole containing the mass of approximately 100 million suns. Not 100 million times the size of our sun, but 100 million times the mass, all compressed into a region smaller than our solar system. The gravitational influence of this central black hole shapes the motion of stars hundreds of thousands of light years away. But here's where the story of Andromeda's size becomes even more mind-bending. The galaxy we can see, with all its trillion stars and vast spiral arms, represents only a fraction of Andromeda's true extent. Surrounding the visible galaxy is something called a dark matter halo, an invisible structure that extends far beyond the farthest visible stars. This dark matter halo may extend for over 1 million light years in all directions, meaning the true Andromeda galaxy is several times larger than what we can actually observe. Dark matter doesn't emit light, doesn't absorb light, and doesn't interact with ordinary matter in ways we can easily detect. Yet it makes up roughly 85% of all matter in the universe. In Andromeda, this invisible dark matter provides the gravitational scaffolding that holds the entire galaxy together. Without it, the outer spiral arms would fly apart, scattered into the void by the centrifugal force of their rotation. Think about this for a moment. Most of Andromeda is invisible to us. We can see the light from its trillion stars. We can observe the glowing gas clouds where new stars are being born. We can detect the radiation from matter falling into its central black hole. But the vast majority of the galaxy's mass and extent remains hidden from our direct observation, detectable only through its gravitational effects on the matter we can see. This invisible component of Andromeda extends our understanding of the galaxy's size in ways that are almost impossible to visualize. If we could somehow see dark matter the way we see ordinary matter, Andromeda would appear as a vast, ghostly sphere surrounding the bright spiral structure we're familiar with. This sphere would be so large that it might extend halfway to our own galaxy, creating a kind of invisible bridge between the two great island universes. The spiral arms of Andromeda themselves tell a story of size and motion that unfolds over hundreds of millions of years. These arms aren't solid structures like the spokes of a wheel. They're more like traffic jams in space, regions where stars and gas become temporarily concentrated as they orbit the galactic center. The spiral pattern rotates, but it rotates at a different speed than the stars themselves. Stars move in and out of the spiral arms over the course of their orbits, sometimes spending tens of millions of years within an arm before moving back into the relatively empty space between arms. This means that Andromeda's spiral structure is constantly changing, constantly evolving. The galaxy you see in photographs taken today is subtly different from the galaxy that existed 100 million years ago. The spiral arms have shifted, new ones have formed, old ones have dissipated. Over the course of cosmic time, Andromeda has likely gone through many different phases, sometimes appearing as a tight, well-defined spiral, other times as a more open, loosely wound structure. Within those spiral arms, star formation proceeds at a pace that dwarfs anything we can truly comprehend. Every year, Andromeda creates approximately one new star. One new nuclear furnace ignites in the depths of space, beginning a life that may last for billions of years. Some of these stars are small and red, destined to burn quietly for trillions of years. Others are massive and blue, living fast and dying young in spectacular supernova explosions that can outshine the entire galaxy for weeks or months. Each of these stars represents a potential solar system, a collection of planets that might harbor conditions suitable for life. With over 1 trillion stars in Andromeda, the number of planets is almost certainly several times that number. Even if only a tiny fraction of these planets are in the right location to support liquid water, even if only a minute percentage of those actually develop life, the numbers become staggering. Andromeda might harbor millions, perhaps billions of worlds, where life has taken hold and begun its own evolutionary journey. This is where contemplating Andromeda's true size becomes not just an exercise in astronomy, but a profound meditation on our place in the cosmic order. Somewhere in that distant galaxy, separated from us by an ocean of space and time, there might be beings looking back toward our Milky Way, wondering about the possibility of life in our corner of the universe. They would see our galaxy as we see theirs, as a faint smudge of light in their night sky, never suspecting that within that smudge, on a small rocky planet orbiting an ordinary yellow star, creatures have evolved the capacity to wonder about them in return. The gravitational interaction between Andromeda and our own galaxy has been shaping both systems for billions of years. Even now, separated by vast distances, the two galaxies are locked in a gravitational embrace that will ultimately determine their fate. This interaction affects not just the overall motion of the galaxies, but the formation and evolution of individual stars and planetary systems within them. As we drift deeper into understanding Andromeda's true scale, we encounter something that challenges our most basic assumptions about what it means for something to be large. You see, when we look at Andromeda through even our most powerful telescopes, we're not seeing the galaxy as it exists today. We're seeing it as it was 2.5 million years ago, when the light that's now reaching our eyes first began its journey across the cosmic void. This means that every measurement we make, every photograph we take, every observation we record, is already ancient history by the time it reaches us. The Andromeda you see in images is younger than our species. It's a galaxy from a time when the most advanced life on Earth consisted of primitive mammals scurrying through forests that would one day become the birthplace of human civilization. But here's where the story becomes even more extraordinary. During those 2.5 million years that light has been traveling from Andromeda to us, the galaxy itself hasn't remained static. It has continued to rotate, to evolve, to change. Stars have been born and died. Entire stellar populations have completed their life cycles. The spiral arms have shifted position. New star-forming regions have ignited, while others have gone dark. This temporal displacement creates a peculiar kind of cosmic archaeology. When we study Andromeda, we're studying the past, examining a galaxy that existed when our own planet was entering an ice age. The beings that might exist in Andromeda today, if they exist at all, are living in a galaxy that has had 2.5 million years to evolve beyond what we can observe. They inhabit a present that remains forever hidden from us, separated not just by distance, but by the fundamental limitation of light speed. Consider the implications of this temporal separation. If there are civilizations in Andromeda that have been trying to communicate with us, their signals left their galaxy when our ancestors were just beginning to develop the cognitive abilities that would eventually lead to language, to writing, to science itself. Any message they sent is still crossing the vast emptiness between our galaxies, carrying information about beings and technologies that may have evolved beyond recognition by the time their signals finally arrive. This time delay also means that our understanding of Andromeda's size is necessarily incomplete. We can measure what we observe, but we cannot know what the galaxy has become in the millions of centuries since that light departed. Has it grown larger through mergers with smaller galaxies? Has it shed mass through gravitational interactions with other members of its local group? Has star formation accelerated or declined? These questions remain unanswerable, hidden behind the cosmic speed limit that governs all information in our universe. The structure of Andromeda extends far beyond what most people imagine when they think of a galaxy. While the bright spiral arms capture our attention in photographs, they represent only the most luminous component of a far more complex system. Scattered throughout the galaxy's vast halo are hundreds of globular clusters, ancient collections of stars that formed when the galaxy was young and the universe itself was a very different place. Each of these globular clusters contains hundreds of thousands of stars packed into spherical regions just a few dozen light years across. To put this density in perspective, if our solar system were located within one of these clusters, our night sky would be ablaze with thousands of stars brighter than Venus, turning night into a kind of eternal twilight. The gravitational interactions between these densely packed stars would create a constantly shifting celestial dance, with some stars being ejected from the cluster entirely, while others spiral inward toward the center. These globular clusters orbit through Andromeda's halo like cosmic satellites, following elliptical paths that carry them far above and below the main galactic disk. Some of these orbits take hundreds of millions of years to complete, meaning that a single globular cluster might witness the galaxy's spiral arms rotate dozens of times during one orbital period. From the perspective of beings living within such a cluster, the main galaxy would appear to slowly evolve and change over cosmic time, its spiral pattern shifting like a vast cosmic pinwheel against the backdrop of distant stars. But even the globular clusters don't represent the full extent of Andromeda's gravitational influence. Recent observations have revealed streams of stars stretching far beyond the galaxy's visible boundaries, trailing remnants of smaller galaxies that were torn apart by Andromeda's immense gravitational field. These stellar streams can extend for hundreds of thousands of light years, creating a complex web of disrupted matter that surrounds the galaxy like cosmic scar tissue. Each of these streams tells a story of galactic cannibalism, of smaller systems that ventured too close to Andromeda and paid the ultimate price. The stars that once formed these satellite galaxies now follow new orbits around their captor, their original galactic homes completely dissolved by tidal forces. This process of galactic merger and disruption has been ongoing for billions of years, gradually building Andromeda into the massive system we observe today. The scale of these disruption events challenges our understanding of what it means for a galaxy to have a definite size. Where exactly does Andromeda end and intergalactic space begin? The answer depends entirely on how you define the boundary. If you consider only the bright spiral disk, Andromeda might appear to have a radius of about 100,000 light years. But if you include the full extent of its dark matter halo and the farthest stellar streams, the galaxy's influence might extend for over 1 million light years in all directions. This ambiguity in defining galactic boundaries reflects a deeper truth about the nature of cosmic structures. Galaxies aren't discrete objects with sharp edges, like islands floating in an empty ocean. They're more like weather systems, with complex shifting boundaries that blend gradually into the surrounding environment. The transition from galaxy to intergalactic space is gradual, marked by steadily decreasing densities of stars and dark matter rather than any clear demarcation line. Within Andromeda's spiral arms, the process of star formation creates regions of extraordinary beauty and violence. Giant molecular clouds, some containing millions of times the mass of our Sun, collapse under their own gravity to form stellar nurseries where dozens or hundreds of new stars ignite simultaneously. These star-forming regions glow with the intense radiation of young massive stars, creating the brilliant pink and blue emission nebulae that make galaxies so photogenic. But star formation is not a gentle process. The massive stars that illuminate these regions burn through their nuclear fuel at prodigious rates, exhausting their energy reserves in just a few million years before exploding as supernovas. These stellar death throes release more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. The shock waves from these explosions compress surrounding gas clouds, triggering new waves of star formation, while simultaneously dispersing heavy elements throughout the galactic disk. This cycle of stellar birth and death has been repeating in Andromeda for over 10 billion years, gradually enriching the galaxy with the carbon, oxygen, silicon, and iron that make rocky planets and complex chemistry possible. The stars visible in Andromeda today represent multiple generations of stellar evolution, each built from the ashes of previous stellar generations. The elements that compose any planets orbiting those distant suns were forged in stellar cores and scattered by supernova explosions, just as the elements in our own bodies were created in stars that died billions of years ago. The magnetic field that permeates Andromeda adds another layer to its complexity and size. This galactic magnetic field, generated by the rotation of ionized gas within the galaxy, extends throughout the spiral arms and beyond, creating invisible structures that guide the motion of charged particles and influence the formation of new stars. The field lines stretch and twist as the galaxy rotates, creating magnetic reconnection events that can accelerate particles to nearly the speed of light. These cosmic magnetic fields are so vast that they dwarf anything we can create or imagine on Earth. A magnetic field line in Andromeda might stretch for thousands of light years, carrying energy and information across distances that would take our fastest spacecraft millions of years to cross. The interaction between these magnetic fields and the galaxy's rotation creates a kind of cosmic dynamo, continuously regenerating the magnetic structure and ensuring its persistence over billions of years. Radio telescopes on Earth can detect the synchrotron radiation emitted by high-energy electrons spiraling along these magnetic field lines, revealing the invisible magnetic skeleton that helps support Andromeda's structure. These observations show that the galaxy's magnetic field extends well beyond the visible spiral arms, creating a magnetic halo that adds yet another dimension to our understanding of the galaxy's true size. The supermassive black hole at Andromeda's center represents perhaps the most extreme example of how size and scale become meaningless when dealing with cosmic objects. This gravitational monster contains the mass of 100 million suns compressed into a region smaller than our solar system. Its event horizon, the boundary beyond which nothing can escape, has a radius of only about 300 million kilometers. By cosmic standards, this is almost infinitesimally small, yet this tiny region controls the behavior of stars and gas clouds hundreds of thousands of light years away. The black hole's gravitational influence shapes the orbital motions of stars throughout the central regions of the galaxy. When matter falls toward the black hole, it forms an accretion disk that heats up to millions of degrees, producing jets of high-energy particles that can extend for thousands of light years beyond the galaxy itself. These relativistic jets represent another way that Andromeda's influence extends far beyond its visible boundaries. The high-energy particles in these jets interact with the intergalactic medium, creating radio-bright structures that can be detected across millions of light years of space. In this sense, the supermassive black hole at Andromeda's center projects the galaxy's presence far into the surrounding cosmic void. As you settle deeper into contemplating these impossible scales, remember that every photon of light reaching us from Andromeda has traveled for longer than our species has existed. Each point of light in that distant spiral carries information about stellar processes, galactic dynamics, and cosmic evolution on scales that stretch the human imagination to its breaking point. We are witnesses to a cosmic drama that unfolds over billions of years, observers of a galactic dance that began long before Earth itself existed, and will continue long after our sun has burned to ash. The rotation of Andromeda itself presents another mind-bending aspect of scale that challenges our terrestrial understanding of motion. The entire galaxy spins like a cosmic pinwheel, but at speeds and timescales that make earthly rotation seem quaint by comparison. The outer edges of Andromeda's spiral arms move at velocities approaching 500 kilometers per second as they orbit the galactic center. To put this in perspective, if you could somehow stand on the edge of one of these spiral arms, you would be traveling fast enough to circle the Earth in just over 2 minutes. Yet despite these incredible velocities, the galaxy's rotation is so vast in scale that it takes approximately 250 million years for the outer regions to complete a single orbit around the center. This means that since the first complex life appeared on Earth, Andromeda has rotated less than 20 times. The galaxy we observe tonight has barely turned through a handful of complete rotations since multicellular organisms first began their evolutionary journey in our planet's ancient oceans. This differential rotation creates one of the most beautiful and mysterious aspects of spiral galaxies. The spiral arms themselves are not rigid structures that rotate as solid units. Instead, they represent density waves that propagate through the galactic disk at their own pace, separate from the motion of individual stars. Stars drift in and out of these spiral arms over the course of their galactic orbits, sometimes spending tens of millions of years within an arm's embrace before emerging into the relative emptiness of interarm space. Imagine watching this process unfold in time-lapse photography spanning hundreds of millions of years. You would see stars flowing through the spiral pattern like water through a cosmic whirlpool, the arms maintaining their shape even as their stellar constituents constantly change. The spiral structure acts as a kind of gravitational traffic jam, temporarily concentrating stars and gas before releasing them to continue their orbital journeys. This dynamic nature of spiral structure adds yet another layer to our understanding of Andromeda's size. The galaxy doesn't just occupy space, it occupies time in ways that are almost impossible to comprehend. The Andromeda we observe represents a snapshot of a constantly evolving system, a single frame from a cosmic movie that has been playing for over 10 billion years. The gas component of Andromeda tells its own story of scale and complexity. Vast clouds of hydrogen and helium permeate the space between stars, creating structures that can span thousands of light years. These interstellar medium clouds are incredibly tenuous by earthly standards, containing only a few atoms per cubic centimeter. Yet their sheer volume makes them massive beyond imagination. A single giant molecular cloud in Andromeda might contain enough gas to form 1 million new stars. These gas clouds don't simply float passively through space. They flow and turbulence in complex patterns driven by stellar winds, supernova shock waves, and the gravitational tides of the galaxy's rotation. The interstellar medium becomes a dynamic, three-dimensional tapestry of density variations, temperature fluctuations, and magnetic field distortions that change on timescales ranging from thousands to millions of years. When we observe Andromeda in different wavelengths of light, we reveal different aspects of this gaseous component. Radio telescopes show us the cold hydrogen that will eventually condense to form new stars. Infrared observations reveal warm dust heated by starlight. X-ray telescopes detect the superhot gas created by stellar explosions and stellar winds. Each wavelength unveils a different layer of the galaxy's structure, like peeling back the layers of an impossibly complex cosmic onion. The dust component of Andromeda adds another dimension to its size and complexity. These microscopic particles, created in the atmospheres of dying stars and dispersed by stellar winds and supernova explosions, form intricate networks throughout the galaxy. Dark lanes visible in optical photographs trace the locations of these dust clouds, creating complex patterns that spiral inward toward the galactic center. This cosmic dust plays a crucial role in the galaxy's ecology. It absorbs starlight and re-emits it at longer wavelengths, helping to cool gas clouds so they can collapse to form new stars. The dust grains also serve as catalysts for chemical reactions that create complex molecules, including some of the organic compounds that are essential for life as we know it. In this sense, the dust lanes of Andromeda represent vast chemical laboratories where the building blocks of complexity are continuously manufactured and dispersed. The three-dimensional structure of these dust lanes creates a labyrinthine network that extends throughout the galactic disk. If you could somehow shrink down and travel through Andromeda's spiral arms, you would navigate through a constantly changing landscape of gas clouds, dust lanes, and stellar associations. Some regions would be brilliantly illuminated by young, massive stars, while others would be shrouded in darkness, lit only by the faint glow of distant stellar populations. The stellar populations within Andromeda themselves represent different epochs in the galaxy's evolution, each telling part of the story of how this massive system assembled over cosmic time. The oldest stars formed when the galaxy was young and the universe was less than 1 billion years old, now populate the central bulge and the outer halo. These ancient suns are metal-poor, composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements. As you move outward from the galactic center, you encounter progressively younger stellar populations, each enriched with more heavy elements than the last. The spiral arms contain the youngest stars, brilliant blue giants that have formed within the last few million years, from gas clouds already enriched by multiple generations of stellar evolution. These young stars burn so brightly that they dominate the galaxy's visible appearance, even though they represent only a tiny fraction of Andromeda's total stellar population. Between these extremes lie stellar populations of every conceivable age and composition, creating a kind of archaeological record of the galaxy's entire history. By studying the colors, brightnesses, and spectra of different stellar groups, astronomers can reconstruct the timeline of Andromeda's assembly, identifying periods of intense star formation, galactic mergers, and evolutionary quiescence. The satellite galaxies that orbit Andromeda add yet another scale to our understanding of this cosmic system. More than a dozen smaller galaxies dance around Andromeda in gravitational attendance, some containing billions of stars, others harboring only a few million. The largest of these satellites, known as M32 and M110, are substantial galaxies in their own right, each containing stellar populations with their own unique histories and characteristics. These satellite galaxies extend Andromeda's gravitational influence across millions of light-years of space. The most distant known satellites orbit at distances of nearly 1 million light-years from the central galaxy, taking billions of years to complete their orbital journeys. From the perspective of beings living in these distant satellites, Andromeda would appear as a brilliant spiral nebula dominating their night sky, its spiral arms clearly visible to the naked eye. The gravitational interactions between Andromeda and its satellites create a complex dynamical system that has been evolving for billions of years. Some satellites are gradually spiraling inward, destined to eventually merge with the central galaxy. Others may be stripped of their outer stars by tidal forces, leaving behind compact remnants that will survive as globular clusters long after their parent galaxies have been destroyed. Recent observations have revealed that many of these satellite galaxies are arranged in a vast, thin disk around Andromeda. suggesting that they may have formed from a single, massive merger event in the galaxy's distant past. This satellite disk extends the organized structure of the Andromeda system far beyond the main galaxy itself, creating a kind of galactic ecosystem that encompasses several million light-years of space. The concept of galactic recycling adds another layer to Andromeda's complexity and demonstrates how the galaxy's influence extends far beyond its visible boundaries. Stars don't simply form and die in isolation. Instead, they participate in a vast cycle of matter and energy exchange that connects stellar evolution to galactic evolution on the largest scales. When massive stars explode as supernovae, they don't just create heavy elements and disperse them into the interstellar medium. They also drive powerful stellar winds that can push gas completely out of the galaxy and into the intergalactic medium. This gas doesn't disappear forever. Over millions of years, it can cool and fall back into the galaxy, carrying with it the chemical enrichment from stellar nucleosynthesis. This galactic fountain effect means that Andromeda is constantly exchanging matter with the space around it, breathing gas in and out like a cosmic lung. The galaxy's true size must therefore include not just the matter currently within its boundaries, but also the vast reservoir of enriched gas that surrounds it in various stages of this recycling process. Some of this expelled gas may travel for millions of light years before eventually returning to the galaxy. During its journey through intergalactic space, this material carries information about Andromeda's stellar populations and chemical evolution to distances far beyond the galaxy's visible extent. In this sense, Andromeda's influence permeates a volume of space many times larger than the galaxy itself. The magnetic field that threads through all of these structures creates an invisible scaffolding that helps organize matter and energy on galactic scales. This magnetic field doesn't simply fill space uniformly. Instead, it forms complex patterns that spiral with the galaxy's rotation, while also responding to the turbulent motions of gas clouds and the explosive energy of stellar death. Charged particles become trapped along these magnetic field lines, creating vast populations of cosmic rays that permeate the entire galaxy. These high-energy particles can travel for millions of years within the galactic magnetic field, gradually diffusing throughout Andromeda's volume while interacting with gas clouds, dust grains, and stellar atmospheres along the way. The magnetic field also plays a crucial role in channeling matter toward the central black hole. As gas spirals inward under gravitational attraction, the magnetic field helps remove angular momentum, allowing material to fall deeper into the gravitational well. This process can accelerate particles to nearly the speed of light, creating the jets and outflows that extend Andromeda's influence far beyond its visible boundaries. When we attempt to measure Andromeda's mass, we encounter another aspect of cosmic scale that challenges our terrestrial intuitions. The visible matter in the galaxy, all the stars and gas clouds we can observe directly, accounts for only about 10% of the galaxy's total mass. The remaining 90% consists of dark matter, an invisible component that reveals itself only through its gravitational effects. This dark matter halo extends far beyond the visible galaxy, creating a gravitational structure that may encompass several million light-years of space. Within this vast dark matter distribution, the visible galaxy represents just the central condensation of ordinary matter, like a bright core within an enormous invisible sphere. The dark matter doesn't simply provide static gravitational support for the galaxy. It participates in the galaxy's dynamics, responding to gravitational perturbations from satellite galaxies and tidal forces from neighboring systems. Computer simulations suggest that this dark matter halo has a complex substructure, with streams and clumps of dark matter flowing through it like invisible rivers and tributaries. Some of these dark matter substructures may contain their own populations of stars, creating faint stellar systems that are almost impossible to detect against the bright background of the main galaxy. Others may be completely dark, containing only dark matter with no ordinary matter at all. These invisible satellites add yet another hidden component to Andromeda's true extent and complexity. As you continue to contemplate these impossible scales, consider that every aspect of Andromeda we've explored represents just a fraction of what remains unknown about this cosmic neighbor. The galaxy exists on scales so vast that light itself takes hundreds of thousands of years just to cross from one side to the other. During that journey, civilizations could rise and fall. Species could evolve and go extinct. Entire planetary systems could form and be destroyed by stellar evolution. Yet even as we struggle to comprehend these scales, we're only beginning to understand how Andromeda fits into the larger cosmic web of galaxies, dark matter, and dark energy that shapes the universe on its largest scales. The galaxy we see is embedded within invisible streams of dark matter that connect it to other galaxies across hundreds of millions of light-years of space. These cosmic filaments create a vast network of gravitational highways along which matter flows between galaxies over cosmic time. Andromeda's size becomes even more mysterious when we consider that the galaxy itself is falling toward us through this cosmic web, guided by gravitational forces that operate on scales encompassing our entire local group of galaxies. The collision that awaits us in 4 billion years is not just the meeting of two isolated systems, but the convergence of two branches of the cosmic web itself. In this larger context, even Andromeda's trillion stars and million light-year extent represent just a single node in a network of structure that spans the observable universe. The true scale of cosmic architecture dwarfs even the most massive galaxies, reminding us that no matter how large something appears, there's always a larger scale waiting to humble our sense of proportion. Tonight, as that faint smudge of light continues its ancient dance across your sky, remember that you're witnessing just the tiniest fraction of a cosmic structure so vast and complex that it challenges the very limits of human imagination. Andromeda's true size encompasses not just space, but time itself, not just matter, but the invisible scaffolding that holds the universe together. Not just what we can see, but all the hidden mysteries that remain beyond our current ability to detect or comprehend. The gravitational choreography that governs Andromeda's motion through space reveals yet another dimension of its incomprehensible scale. As this galaxy hurtles toward us at 250,000 miles per hour, it's not traveling through empty space, but through a medium far more complex and mysterious than we might imagine. The intergalactic medium between Andromeda and our own galaxy contains wispy traces of hydrogen gas, remnant radiation from the early universe, and invisible streams of dark matter that create highways of gravitational influence spanning millions of light years. These intergalactic bridges of matter represent connections between galaxies that existed long before Either system developed their current spiral structure. In the early universe, when Andromeda and the Milky Way were young, chaotic collections of gas and dark matter, tendrils of material stretched between them like cosmic spiderwebs. Over billions of years, these connections have been stretched and attenuated by the expansion of space itself, but they haven't disappeared entirely. Current observations suggest that faint streams of hydrogen gas still connect our galaxy to Andromeda, creating a kind of umbilical cord between the two systems. This gas is so tenuous that it contains fewer atoms per cubic meter than the best vacuum we can create on Earth, yet its total mass may exceed that of millions of stars. As Andromeda approaches, this connecting material will become compressed and heated, potentially triggering bursts of star formation long before the galaxies themselves begin to merge. The concept of galactic weather adds another layer to understanding Andromeda's true extent. Just as Earth has atmospheric systems that transport energy and matter across continents, Andromeda experiences galactic-scale weather patterns that move gas, dust, and magnetic fields across thousands of light years. These cosmic weather systems operate on timescales of millions of years, creating storms of star formation that can persist longer than complex life has existed on Earth. Stellar winds from massive stars create vast bubbles of superheated gas that expand through the interstellar medium like cosmic hurricanes. When these bubbles collide and merge, they create turbulent mixing that can transport material from the galactic center to the outer edges of the spiral arms. The energy from these stellar winds is so enormous that it can literally blow holes in the galaxy's disk, creating channels through which gas can flow from one side of the galactic plane to the other. Supernova explosions act like cosmic thunderstorms, each one releasing more energy in a few seconds than our sun will produce in its entire lifetime. These explosions create shock waves that propagate through the interstellar medium for millions of years, compressing gas clouds in some regions while evacuating matter from others. The accumulated effect of thousands of these stellar explosions over cosmic time has created a complex three-dimensional structure within Andromeda's disk, with vast cavities surrounded by dense shells of compressed gas. The magnetic field that permeates Andromeda participates in this galactic weather system, creating invisible storm fronts where different magnetic regions collide and reconnect. These magnetic reconnection events can accelerate particles to incredible energies, creating cosmic ray storms that propagate throughout the galaxy. The charged particles in these cosmic ray storms follow the magnetic field lines like invisible highways, carrying energy and information across the entire galactic system. But perhaps the most mind-bending aspect of Andromeda's scale emerges when we consider its relationship to time itself. The galaxy we observe tonight represents a snapshot frozen in cosmic amber, preserved by the time it takes light to cross the vast distances of space. Every region of Andromeda we can see exists at a slightly different moment in the past, creating a kind of temporal mosaic where different parts of the galaxy are observed at different ages. The light from Andromeda's center left the galaxy about 10,000 years before the light from its outer edges, meaning we're simultaneously observing the galaxy as it existed at thousands of different moments in its history. This temporal smearing effect becomes more pronounced as we look at larger and more distant objects. But even within a single galaxy like Andromeda, we're witnessing a composite image assembled from light that departed at different times across a span of hundreds of thousands of years. This temporal complexity means that Andromeda's true size must be understood not just in terms of spatial extent, but also in terms of temporal depth. The galaxy exists as a four-dimensional object, stretched across both space and time, with each photon of light carrying information about a specific location at a specific moment in the galaxy's evolution. When we study Andromeda, we're not just looking at a distant object, we're excavating layers of cosmic history preserved in the light that has been traveling toward us for millions of years. The stellar nurseries within Andromeda's spiral arms represent some of the most violent and creative environments in the galaxy. These star-forming regions can span hundreds of light years and contain enough raw material to create thousands of new solar systems. The process of star formation itself operates on scales that dwarf anything in our terrestrial experience, with shock waves from nearby supernovas triggering the collapse of gas clouds that may be larger than our entire solar system. Within these collapsing clouds, gravity battles against the thermal energy of the gas in a cosmic struggle that can last for millions of years. As the cloud contracts, it fragments into smaller and smaller pieces, each destined to become an individual star or stellar system. The largest fragments become massive stars that will burn brilliantly for just a few million years before exploding as supernovas. The smallest fragments become red dwarf stars that will burn quietly for trillions of years, long after galaxies like Andromeda have completed their evolution and begun their final decline. The energy released during these star formation events is so enormous that it can be detected across intergalactic distances. When a particularly massive star formation region ignites in Andromeda, it can outshine billions of older, quieter stars, creating bright knots of light that are visible even in small telescopes. These stellar fireworks represent the galaxy's ongoing process of renewal, constantly creating new stars to replace those that have exhausted their nuclear fuel and died. The chemical evolution of Andromeda adds another dimension to its complexity that unfolds over cosmic time. When the galaxy first formed, it contained almost exclusively hydrogen and helium, the primordial elements created in the Big Bang. Every heavier element that exists in Andromeda today, from the carbon in organic molecules to the iron in planetary cores, was manufactured in the nuclear furnaces of previous stellar generations. This process of cosmic alchemy has been ongoing for over 10 billion years, gradually enriching Andromeda's interstellar medium with the elements necessary for complex chemistry and, potentially, life itself. The outer regions of the galaxy, where star formation began later and has proceeded more slowly, still contain relatively primitive gas with low concentrations of heavy elements. The inner regions, where stellar evolution has been more rapid and intense, have been thoroughly enriched with the products of stellar nuclear synthesis. This chemical gradient creates a kind of archaeological record spanning the entire galaxy. By studying the composition of stars in different regions of Andromeda, astronomers can reconstruct the timeline of the galaxy's chemical evolution and identify periods when star formation was particularly active or quiescent. The most metal-rich regions near the galactic center tell a story of intense stellar recycling, while the metal-poor outer halo preserves information about the galaxy's earliest epochs. The globular clusters that populate Andromeda's halo represent some of the oldest stellar systems in the galaxy. Fossil remnants from an era when the universe itself was young and galaxies were just beginning to assemble from the cosmic web of dark matter. These ancient stellar cities contain hundreds of thousands of stars packed into spherical regions just a few dozen light-years across, creating stellar densities that are millions of times greater than what we experience in our local neighborhood. If our solar system were located within one of Andromeda's globular clusters, the night sky would be transformed beyond recognition. Thousands of stars would shine brighter than Venus, turning night into a kind of eternal twilight, illuminated by a stellar canopy of impossible beauty. The gravitational interactions between these densely packed stars would create a constantly shifting celestial dance, with stellar encounters occurring frequently enough to dramatically alter planetary orbits and potentially strip planets from their parent stars entirely. These globular clusters follow highly elliptical orbits that carry them far above and below Andromeda's main disk, creating a three-dimensional halo of ancient stellar systems that extends the galaxy's structure across millions of cubic light-years of space. During their orbital journeys, these clusters occasionally pass through the galactic disk, potentially triggering bursts of star formation through gravitational interactions with the spiral arms. The dark matter halo that surrounds and permeates Andromeda represents perhaps the most mysterious component of the galaxy's structure. This invisible scaffolding contains roughly 10 times more mass than all the visible matter combined, yet it reveals itself only through its gravitational effects on the stars and gas we can observe directly. The dark matter doesn't emit light, doesn't absorb light, and doesn't interact with ordinary matter through any of the familiar forces except gravity. Computer simulations of dark matter evolution suggest that Andromeda's halo has a complex internal structure, with dense subhalos, tidal streams, and caustic surfaces, created by the gravitational interactions of countless dark matter particles over cosmic time. Some of these substructures may contain their own populations of stars, creating faint dwarf galaxies that orbit within the larger dark matter distribution, like cities within a vast invisible continent. The boundary between Andromeda's dark matter halo and the intergalactic medium is not sharp but gradual, with dark matter density decreasing slowly with distance from the galactic center. At some point, perhaps a million light-years from the visible galaxy, Andromeda's dark matter halo blends into the cosmic web of dark matter filaments that connect all galaxies across the universe. In this sense, Andromeda doesn't have a definite edge, but gradually fades into the larger dark matter structure that shapes cosmic evolution on the largest scales. Recent observations have revealed that Andromeda's dark matter halo may be surrounded by a vast corona of hot, diffuse gas heated to millions of degrees by gravitational compression and shock waves from infalling material. This corona extends far beyond the visible galaxy and may contain as much mass as all the stars in the galactic disk combined. The gas in this corona is so hot and tenuous that it's nearly invisible to optical telescopes, detectable only through its X-ray emission and its gravitational effects on more distant objects. The existence of this galactic corona adds yet another layer to Andromeda's true size and complexity. The corona serves as a reservoir of material that can eventually cool and fall into the galaxy, fueling continued star formation for billions of years to come. It also acts as a kind of galactic atmosphere, mediating the exchange of matter and energy between the galaxy and the surrounding intergalactic medium. Within this corona, vast streams of gas flow inward and outward, driven by the complex interplay between gravitational attraction and the energy released by stellar evolution. Some of this gas has been enriched with heavy elements during previous episodes of star formation, while other components represent relatively pristine material falling into the galaxy for the first time since the early universe. The magnetic field that threads through Andromeda's corona creates invisible channels that guide the flow of charged particles and help organize the structure of this diffuse gas. Magnetic field lines can extend for hundreds of thousands of light years, creating connections between the galaxy's disk and its outermost regions. These magnetic highways allow energy and matter to flow between different components of the galactic system, coupling the evolution of the central galaxy to processes occurring in its extended halo. The rotation of Andromeda's disk drags the magnetic field lines into a spiral pattern that mirrors the galaxy's visible structure. This magnetic spiral extends far beyond the optical disk, creating a kind of invisible extension of the spiral arms that may influence the behavior of gas and cosmic rays throughout the galactic halo. The interaction between rotation and magnetic fields also generates electrical currents on galactic scales, creating a kind of cosmic dynamo that maintains the magnetic field structure over billions of years. As we continue to explore the implications of Andromeda's true size, we encounter questions that probe the very nature of cosmic structure and evolution. How do galaxies like Andromeda maintain their coherent spiral patterns over billions of years? What role does dark matter play in shaping galactic evolution? How do the processes occurring within individual galaxies connect to the larger scale structure of the cosmic web? These questions remind us that Andromeda's size cannot be understood in isolation, but must be considered within the context of cosmic evolution as a whole. The galaxy we observe today is the product of over 10 billion years of gravitational assembly, stellar evolution, and chemical enrichment. Every component of its structure, from the central black hole to the outermost dark matter subhalos, tells part of the story of how cosmic structure emerged from the nearly uniform conditions of the early universe. The collision that awaits Andromeda and our own galaxy in 4 billion years will represent the culmination of this cosmic story, at least for our local corner of the universe. When these two massive systems finally merge, they will create something entirely new. A giant elliptical galaxy that astronomers have already nicknamed Milomeda. This future galaxy will be larger than either of its progenitors, with a more extended distribution of stars and a fundamentally different structure. The process of galactic merger will reshape both systems beyond recognition, flinging some stars into the vast emptiness between galaxies, while gathering others into the dense core of the new combined system. The supermassive black holes at the centers of both galaxies will eventually spiral into each other and merge, creating gravitational waves that will ripple through space-time with energies that dwarf the total luminous output of all the stars in both galaxies combined. But this cosmic collision is still billions of years in the future, an almost incomprehensibly long time compared to any human timescale. During those billions of years, Andromeda will continue to evolve, to form new stars, to accumulate material from its surroundings, and to gradually change its structure and appearance. The galaxy we observe tonight represents just one moment in this vast evolutionary story, a snapshot of a dynamic system caught in the act of cosmic becoming. As you drift deeper into contemplation of these impossible scales, remember that every photon reaching your eye from Andromeda has been traveling through space since before our species existed, carrying information about stellar processes and galactic dynamics that operate on scales beyond anything in human experience. The light you see tonight began its journey when our planet was inhabited by entirely different forms of life, when the continents were arranged differently, when the climate and chemistry of Earth's atmosphere bore little resemblance to the world we know today. In this sense, observing Andromeda is an act of cosmic archaeology, excavating information about the deep past that has been preserved in the light crossing the vast emptiness between galaxies. We are time travelers using photons as our vehicle, journeying backward through cosmic history to witness the universe as it existed when it was younger, more dynamic, and filled with the violent energy of galactic youth. The true size of Andromeda encompasses not just the spatial dimensions we've explored tonight, but also this temporal dimension that connects us to the deep past of cosmic evolution. The galaxy exists simultaneously as a present-day system of stars and gas, and as an archaeological record of billions of years of stellar birth, stellar death, and galactic evolution. In studying Andromeda, we glimpse both the universe as it was and the cosmic processes that will shape its future evolution across timescales that challenge the human imagination. Tonight, as you continue to contemplate that faint smudge of light in the constellation Andromeda, know that you are witnessing one of the most magnificent structures in the known universe. A trillion-star city of light spanning hundreds of thousands of light years, embedded within invisible scaffolding of dark matter that extends across millions of light years of space, surrounded by coronas of hot gas and threading magnetic fields that connect it to the cosmic web itself. This is how big Andromeda really is, not just in terms of the stars we can count or the distances we can measure, but in terms of the profound cosmic story it tells about the nature of structure, time, and scale in our universe. And we've only begun to scratch the surface of this cosmic mystery. The story of Andromeda's size becomes even more extraordinary when we consider the galaxy's relationship with time on scales that stretch beyond human comprehension. While we've explored its spatial dimensions, the temporal aspects of this cosmic giant reveal layers of complexity that challenge our understanding of what it means for something to exist across billions of years. Consider this remarkable fact. The oldest stars in Andromeda began shining when the universe was less than 1 billion years old, when space itself was smaller, denser, and filled with the raw energy of cosmic youth. These ancient suns have been burning steadily for over 10 billion years, witnessing the entire evolution of their galaxy from a chaotic collection of gas clouds into the magnificent spiral structure we observe today. During their impossibly long lives, these stellar elders have watched countless generations of younger stars ignite, burn brilliantly, and die in spectacular explosions. They've seen the chemical composition of their galaxy transform from the pristine hydrogen and helium of the early universe into the rich mixture of elements that makes complex chemistry and potentially life possible. They are living witnesses to cosmic history on scales that dwarf anything in human experience. But even these ancient stars represent only the middle chapters of Andromeda's story. The dark matter scaffolding that holds the galaxy together began forming when the universe was even younger, during an epoch when the first structures were condensing out of the primordial cosmic web. This invisible framework has been slowly accumulating matter for nearly 14 billion years, growing from tiny quantum fluctuations in the early universe into the massive gravitational architecture that now supports 1 trillion stars. The growth of this dark matter halo occurred through a process cosmologists call hierarchical assembly, where smaller structures gradually merge to form larger ones over cosmic time. What we see as Andromeda today represents the accumulated result of countless mergers between smaller dark matter halos, each bringing its own population of stars, gas, and smaller satellite galaxies into the growing system. Archaeological evidence of this assembly process remains visible today in the form of stellar streams and tidal debris scattered throughout Andromeda's halo. These ghostly remnants of disrupted satellite galaxies tell stories of cosmic violence and gravitational cannibalism that unfolded over billions of years. Each stream represents a smaller galaxy that ventured too close to Andromeda and was torn apart by tidal forces, its stars redistributed into long, thin trails that now orbit the larger system like cosmic fossils. Recent surveys have identified dozens of these stellar streams threading through Andromeda's halo, each one preserving information about a merger event that occurred millions or billions of years ago. The stars in these streams carry chemical signatures that reveal the nature of their parent galaxies, allowing astronomers to reconstruct the feeding history of this cosmic monster and understand how it grew to its current enormous size. The spiral arms themselves tell a story of pattern formation and maintenance that operates on timescales spanning hundreds of millions of years. These graceful curves aren't permanent features etched into the galaxy's structure. Instead, they represent dynamic density waves that propagate through the galactic disk, temporarily concentrating stars and gas before releasing them to continue their orbital journeys. The mathematics governing these spiral density waves reveals something profound about the relationship between order and chaos on cosmic scales. Despite the violent stellar explosions, chaotic gas motions, and gravitational perturbations that constantly disturb the galactic disk, the spiral pattern maintains its coherent structure for billions of years. This represents a kind of cosmic self-organization where the collective behavior of billions of stars creates emergent patterns that are far more stable and long-lived than any individual component. The persistence of Andromeda's spiral structure also depends on its interactions with the surrounding environment. Gravitational torques from satellite galaxies, tidal forces from neighboring systems, and even the inflow of fresh gas from the intergalactic medium all contribute to maintaining the spiral pattern. In this sense, the galaxy's beautiful structure emerges from its ongoing dialogue with the cosmic web itself. Within the spiral arms, the process of stellar recycling operates on cycles that span multiple stellar generations. Massive stars form, live brief but brilliant lives, and explode as supernovas, enriching the interstellar medium with heavy elements while simultaneously triggering new waves of star formation through their shock waves. This process has been repeating for billions of years, gradually increasing the metallicity of the galaxy and creating the complex chemical gradients we observe today. The efficiency of this stellar recycling process varies dramatically across different regions of Andromeda. In the dense central regions, where stellar densities are highest and supernovas are most frequent, the interstellar medium has been thoroughly enriched with heavy elements. Gas clouds in these regions, contain significant quantities of carbon, oxygen, silicon, and iron, providing the raw materials necessary for rocky planet formation and complex organic chemistry. Moving outward through the spiral arms, the degree of chemical enrichment decreases gradually, creating a metallicity gradient that reflects the galaxy's inside-out formation history. The outermost regions of Andromeda's disk still contain relatively pristine gas with compositions more similar to the early universe, while the innermost regions show the accumulated effects of billions of years of stellar nucleosynthesis. This chemical evolution connects Andromeda's past to its potential future in ways that are both profound and speculative. If life has emerged anywhere within this vast galaxy, it most likely occurred in regions where the interstellar medium has been sufficiently enriched with heavy elements to allow the formation of terrestrial planets and complex organic molecules. The chemical gradients within Andromeda create a kind of habitability gradient, with different regions offering different prospects for the emergence and evolution of complex life. The central bulge of Andromeda represents perhaps the most extreme environment within the galaxy, where stellar densities reach levels that would transform the night sky beyond recognition. In the dense core regions, stars are packed so closely together that gravitational interactions frequently alter their orbits, sometimes flinging them out of the galaxy entirely, or sending them spiraling inward toward the central black hole. The supermassive black hole at Andromeda's heart adds another dimension of scale that challenges our understanding of how such extreme objects form and evolve. With a mass equivalent to 100 million suns, this gravitational monster represents one of the most massive black holes known in the local universe. Its event horizon, while tiny compared to galactic scales, marks a boundary beyond which the normal rules of space and time break down entirely. The formation of such a massive black hole requires either the direct collapse of enormous gas clouds in the early universe or the gradual growth of smaller black holes through accretion and mergers over cosmic time. Current theories suggest that Andromeda's central black hole likely grew through both processes, beginning as a massive seed in the galaxy's youth and continuing to accumulate matter through billions of years of galactic evolution. The gravitational influence of this central black hole extends throughout the galaxy's innermost regions, affecting the orbits of stars tens of thousands of light-years away. When gas falls toward the black hole, it forms an accretion disk that heats up to millions of degrees, sometimes producing jets of high-energy particles that can extend far beyond the galaxy itself. These relativistic jets represent another way that Andromeda's influence reaches across vast distances, projecting the galaxy's presence deep into the surrounding intergalactic medium. The interaction between Andromeda's central black hole and the surrounding stellar population creates a complex dynamical environment where stellar orbits can become highly elongated or even chaotic. Some stars follow stable orbits that bring them close to the black hole on regular schedules, while others follow more erratic paths that may eventually result in tidal disruption events where the star is torn apart by the black hole's immense gravity. These tidal disruption events, while rare, produce some of the most luminous and energetic phenomena in the galaxy. When a star ventures too close to the central black hole, the difference in gravitational force between the side of the star facing the black hole and the side facing away becomes so large that it overcomes the star's own gravity, stretching the star into a long stream of plasma that spirals into the accretion disk. The energy released during these events can briefly outshine the entire galaxy, creating flares of radiation that are detectable across intergalactic distances. These stellar death throes provide astronomers with unique opportunities to study the properties of supermassive black holes and the extreme physics that operates in their vicinity. Beyond the central regions, Andromeda's disk contains stellar populations that span the entire age of the galaxy, creating a kind of temporal cross-section through cosmic history. The oldest disk stars formed when the galaxy was still assembling from smaller components, while the youngest stars in the spiral arms have ignited within the last few million years from gas clouds that have been enriched by multiple generations of stellar evolution. This age diversity creates complex patterns of stellar motion that reflect the galaxy's dynamical history. Older stellar populations have had more time to be scattered by gravitational perturbations, creating a thicker, more diffuse distribution around the galactic plane. Younger populations remain more tightly concentrated within the thin disk, creating the layered structure that gives spiral galaxies their characteristic appearance when viewed edge-on. The vertical structure of Andromeda's disk reveals information about the galaxy's heating history, the accumulated effects of stellar explosions, gravitational encounters, and interactions with satellite galaxies over cosmic time. Each generation of stars carries kinematic information about the gravitational environment that existed when it formed, allowing astronomers to reconstruct the timeline of dynamical evolution within the galactic disk. The outer regions of Andromeda's disk fade gradually into the inner halo, creating a transition zone where stellar densities decrease exponentially with radius. This outer disk region contains some of the galaxy's most metal-poor stars, ancient objects that formed from relatively pristine gas during the early stages of galactic assembly. These stellar fossils preserve information about the chemical composition of the early universe and the initial conditions that governed galaxy formation. Extended surveys of Andromeda's outer regions have revealed that the galaxy's stellar distribution continues far beyond what was previously thought to be its edge. Faint stellar populations have been detected at distances exceeding 200,000 light-years from the galactic center, pushing the boundary of Andromeda's visible extent well beyond its traditional definition. These extended stellar halos likely formed through the accretion and disruption of satellite galaxies over cosmic time. As smaller systems fell into Andromeda's gravitational well, their outer stars were stripped away by tidal forces and redistributed into the growing halo. The current stellar halo represents the accumulated debris from billions of years of hierarchical assembly, a kind of archaeological record of the galaxy's feeding history. The chemical compositions of halo stars provide clues about the nature of the accreted satellite galaxies and the timeline of assembly events. Different stellar populations within the halo show distinct chemical signatures that can be linked to specific merger events or to the disruption of particular types of satellite systems. Some regions of the halo contain stellar populations with chemical compositions that don't match any known type of galaxy in the local universe, suggesting that Andromeda accreted satellite systems whose properties were very different from the dwarf galaxies we observe today. These chemical anomalies provide windows into the early stages of galaxy formation, when the universe was younger and galaxy types may have been more diverse than what we see in the present-day cosmic environment. The globular cluster system that populates Andromeda's halo adds another layer of complexity to our understanding of the galaxy's size and structure. With over 400 known globular clusters, Andromeda hosts one of the richest cluster systems in the local universe. These ancient stellar cities follow highly elliptical orbits that carry them throughout the galaxy's halo, creating a three-dimensional network of gravitationally bound stellar populations. The orbital properties of these globular clusters provide information about the mass distribution within Andromeda's halo, including both the visible stellar component and the invisible dark matter component. By tracking the motions of globular clusters over time, astronomers can map the gravitational potential of the galaxy and constrain the properties of its dark matter halo. Some of Andromeda's globular clusters show evidence of multiple stellar populations, suggesting complex formation histories that may involve multiple episodes of star formation or the merger of smaller cluster systems. These multi-population clusters provide insights into the early stages of cluster formation and the environmental conditions that existed when the galaxy was young. The spatial distribution of globular clusters within Andromeda's halo also reveals information about the galaxy's assembly history. Different populations of clusters show different spatial distributions and orbital properties, suggesting that they were accreted at different times or from different types of progenitor systems. The metal-rich clusters are more centrally concentrated and follow more circular orbits, while the metal-poor clusters have a more extended distribution and follow more eccentric paths. This dichotomy in globular cluster properties reflects the two-phase formation history that characterizes most large galaxies. The metal-rich clusters likely formed in situ during the early collapse of the galaxy's central regions, while the metal-poor clusters were probably accreted along with satellite galaxies during later merger events. The total mass contained within Andromeda's globular cluster system represents only a tiny fraction of the galaxy's total stellar mass. Yet these clusters serve as important traces of the galaxy's gravitational potential and formation history. Their long orbital periods and resistance to tidal disruption make them ideal probes of the galaxy's extended structure and dark matter distribution. Recent observations have revealed that some of Andromeda's globular clusters are embedded within stellar streams, confirming their association with disrupted satellite galaxies. These stream cluster associations provide direct evidence for the hierarchical assembly process and help astronomers identify which stellar debris features originated from specific accretion events. The kinematics of globular clusters also constrain models of Andromeda's dark matter halo structure. Different dark matter profiles predict different cluster velocity distributions, allowing observers to test theoretical predictions about how dark matter halos form and evolve over cosmic time. These tests represent some of the most stringent constraints available on the nature of dark matter and its role in galaxy formation. As we continue to explore the implications of Andromeda's true size, we encounter questions that connect galactic astronomy to fundamental physics and cosmology. How do the properties of individual galaxies like Andromeda relate to the larger scale structure of the universe? What role do galaxies play in the cosmic web of dark matter and dark energy that shapes the evolution of the universe as a whole? These questions remind us that Andromeda's enormous size and complexity cannot be understood in isolation, but must be considered within the context of cosmic evolution on the largest scales. The galaxy we observe today is both a product of cosmic history and an active participant in ongoing cosmic processes that will continue to shape its evolution for billions of years to come. The approaching collision between Andromeda and our own Milky Way represents just one example of the ongoing dynamical evolution that characterizes the universe on all scales. This merger will redistribute the matter and energy contained within both galaxies, potentially triggering new episodes of star formation, while fundamentally altering the structure of both systems. But even this dramatic event represents just a small perturbation in the larger cosmic story. The merged galaxy that results from this collision will continue to evolve, to accrete new material from its surroundings, and to participate in the ongoing assembly of ever larger structures within the cosmic web. On the largest scales, groups and clusters of galaxies, like the one that contains Andromeda, are themselves falling toward even more massive structures, creating a hierarchy of gravitational assembly that extends from individual stars all the way up to the largest observable structures in the universe. Andromeda's motion through space reflects not just its interaction with our own galaxy, but its participation in these larger-scale flows that shape cosmic evolution on scales spanning hundreds of millions of light-years. The dark energy that drives the accelerating expansion of the universe adds another layer of complexity to this cosmic story. As space itself expands at an ever-increasing rate, the largest structures in the universe are being stretched apart, eventually isolating galaxy groups and clusters from each other across vast distances. In the far future, the local group containing Andromeda and the Milky Way may become completely isolated from the rest of the observable universe, creating a kind of cosmic island surrounded by empty space. This cosmic isolation will fundamentally change the nature of astronomy for any civilizations that might exist in the far future. The expanding universe will carry most galaxies beyond the cosmic horizon, making them forever unobservable and erasing the evidence for cosmic expansion itself. Future astronomers living billions of years from now may have no way to discover that the universe is expanding, or that it began with a Big Bang. In this context, our current observations of Andromeda and other distant galaxies represent a unique window into cosmic history that will not remain open forever. We are living during a special epoch when the universe is old enough for complex structures to have formed, but young enough for distant galaxies to remain visible. The light we see from Andromeda tonight carries information about cosmic processes and galactic evolution that may become permanently inaccessible to future generations. This temporal perspective adds another dimension to our appreciation of Andromeda's true size and significance. The galaxy represents not just a massive collection of stars and dark matter, but a messenger from the cosmic past that connects us to the deep history of structure formation in the universe. Every photon reaching us from Andromeda carries information that has been traveling for over 2 million years, preserving details about stellar evolution, chemical enrichment, and galactic dynamics from an epoch when our own species was just beginning to emerge. As you settle deeper into contemplation of these cosmic scales and timescales, remember that Andromeda's story is ultimately connected to our own. The atoms in your body were forged in stellar furnaces, not unlike those burning in Andromeda today. The gravitational processes that shaped Andromeda's structure operate according to the same physical laws that govern the motion of planets in our solar system and the chemistry of life on Earth. We are participants in the same cosmic story that gave birth to Andromeda and billions of other galaxies throughout the observable universe. Our ability to observe and study this distant galaxy represents a remarkable achievement of cosmic evolution itself, the emergence of conscious beings capable of contemplating their own cosmic context and place within the vast tapestry of space and time. The true size of Andromeda encompasses all of these dimensions, spatial and temporal, visible and invisible, physical and philosophical. It is simultaneously a concrete astronomical object that we can measure and study, and a symbol of the profound mysteries that continue to challenge our understanding of the universe and our place within it. Tonight, as that ancient light continues its journey from Andromeda to your eyes, you are witnessing one of the most magnificent examples of cosmic architecture in the known universe. A structure so vast that light takes hundreds of thousands of years to cross from one side to the other, so massive that it contains more stars than there are grains of sand on all the beaches of Earth, and so old that it has been shining since before our planet existed. This is how big Andromeda really is, measured not just in light years or stellar masses, but in the profound connections it reveals between the cosmic past and the cosmic future, between the smallest scales of atomic physics and the largest scales of cosmological structure, between the deep mysteries of dark matter and dark energy, and the emergence of complexity and consciousness in our universe. The story of Andromeda's size becomes even more profound when we consider the galaxy's hidden architecture, the invisible scaffolding that extends far beyond anything we can directly observe. Surrounding the brilliant spiral we see in photographs lies a vast ecosystem of gravitational influence that may stretch across several million light-years of space, creating connections and interactions that dwarf even our most ambitious attempts to comprehend cosmic scale. Within this extended realm, streams of ancient stars follow ghostly orbits that carry them on journeys lasting billions of years. These stellar wanderers represent the remnants of smaller galaxies that were captured and consumed by Andromeda's immense gravitational appetite over cosmic time. Each stream tells a story of cosmic violence and transformation, of entire galactic communities that were torn apart and redistributed into the growing web of Andromeda's influence. But perhaps the most humbling aspect of Andromeda's true extent lies in what we cannot see at all. The dark matter component that dominates the galaxy's mass creates gravitational structures that may extend 10 times farther than the farthest visible stars. This invisible realm operates according to rules we're only beginning to understand, governed by particle physics that remains largely mysterious despite decades of intensive research. Imagine trying to map a vast city at night, but you can only see the streetlights. The buildings, the roads, the infrastructure that gives the city its shape and function remain hidden in darkness. That's our situation with Andromeda. The stars we observe represent only the illuminated portions of a far more complex gravitational metropolis that extends into realms we can barely detect. The magnetic fields threading through this cosmic architecture add another layer of invisible complexity. These fields, generated by the rotation of charged particles within the galaxy, create highways for cosmic ray propagation that span the entire galactic system. High-energy particles accelerated by stellar explosions and black hole activity follow these magnetic field lines like traffic on cosmic freeways, carrying energy and information across distances that would take light itself thousands of years to traverse. Recent computer simulations suggest that Andromeda's magnetic field may form intricate knots and loops that channel matter and energy in ways we're only beginning to appreciate. These magnetic structures can persist for millions of years, creating semi-permanent features in the galaxy's electromagnetic landscape that influence everything from star formation rates to the paths of cosmic ray particles. The interaction between Andromeda's magnetic field and the solar wind from its trillion stars creates a complex electromagnetic environment that varies dramatically across different regions of the galaxy. Near the central black hole, magnetic field strengths may reach levels that would instantly disrupt any technological civilization, while in the outer halo, field strengths drop to levels weaker than Earth's own magnetic field. This electromagnetic variation creates different zones within the galaxy, where different physical processes dominate. In the magnetized central regions, charged particles spiral along field lines in complex helical patterns, while in the weakly magnetized outer regions, cosmic rays can propagate more freely, creating a more isotropic radiation environment. The temporal evolution of Andromeda's magnetic field adds another dimension to our understanding of galactic size and complexity. The field structure we observe today represents the accumulated result of billions of years of galactic rotation, stellar evolution, and magnetic reconnection events. The galaxy's magnetic memory preserves information about past episodes of intense star formation, major merger events, and interactions with the intergalactic medium. Magnetic field reversals, similar to those that occur in Earth's magnetic field but on vastly larger scales, may periodically restructure the entire galactic electromagnetic environment. These reversals could have profound effects on cosmic ray propagation, stellar wind interactions, and even the chemistry of star-forming regions throughout the galaxy. The boundary between Andromeda and the surrounding intergalactic medium becomes even more complex when we consider the galaxy's extended atmosphere of hot, ionized gas. This galactic corona, heated to temperatures of millions of degrees by gravitational compression and shock waves from stellar explosions, may contain as much mass as all the visible stars in the galaxy's disk. This hot corona acts as a kind of galactic breathing system, mediating the exchange of matter and energy between the galaxy and its surroundings. Gas falling into the galaxy from the cosmic web must pass through this corona, where it's heated, ionized, and chemically processed before eventually cooling and condensing into the star-forming regions of the disk. The corona also serves as a reservoir for future star formation, containing vast quantities of enriched gas that will eventually cool and fall back into the galaxy over the course of billions of years. This recycling process ensures that Andromeda will continue forming new stars long into the cosmic future, even as the universe around it continues to expand and cool. Observations of this coronal gas require specialized X-ray telescopes capable of detecting the faint emission from million-degree plasma. These observations reveal complex temperature and density structures within the corona, including streams of cooling gas, shock fronts from satellite galaxy interactions, and cavities blown out by energetic outflows from the central black hole. The chemical composition of Andromeda's corona tells a story of galactic evolution that spans billions of years. Elements like oxygen, neon, and iron detected in the hot gas were manufactured in stellar cores and dispersed by supernova explosions, then heated and ionized as they joined the coronal environment. The abundance patterns observed in the corona reflect the integrated history of stellar nucleosynthesis throughout the galaxy. Different regions of the corona show different levels of chemical enrichment, creating a three-dimensional map of how stellar ejecta have been distributed throughout the galaxy's extended atmosphere. This chemical archaeology allows astronomers to reconstruct the timeline of major star formation episodes and identify regions where particularly intense stellar evolution has occurred. The interaction between Andromeda's corona and the streams of satellites falling into the galaxy creates complex hydrodynamical phenomena that are only now being understood through sophisticated computer simulations. As satellite galaxies plunge through the hot corona, they create shock waves and turbulent wakes that can persist for hundreds of millions of years. These interactions can strip gas from the infalling satellites while simultaneously compressing and heating the coronal gas, creating a complex feedback loop that influences both the evolution of the satellite systems and the structure of the galaxy's extended atmosphere. The end result is a constantly evolving ecosystem of gas, stars, and dark matter that operates on scales far larger than the visible galaxy. The gravitational influence of Andromeda extends even beyond its dark matter halo through its interaction with the cosmic web itself. The galaxy sits at the intersection of several dark matter filaments that connect it to other massive structures across hundreds of millions of light years. These cosmic highways channel matter and energy between galaxies, creating a vast network of gravitational influence that shapes the evolution of entire regions of the universe. Along these filaments, streams of dark matter and diffuse gas flow between Andromeda and its neighbors, carrying information about conditions in distant parts of the cosmic web. Some of this material will eventually join Andromeda's halo, while other components will continue their journey to even more distant destinations, spreading the galaxy's gravitational influence across vast cosmic distances. The approaching collision with our own Milky Way represents just one example of the ongoing interactions that characterize galaxy evolution within the cosmic web. As Andromeda and the Milky Way fall toward each other along one of these dark matter filaments, they're following a gravitational script that was written into the cosmic web billions of years ago. This collision will fundamentally alter the local cosmic web structure, redirecting matter flows and creating new patterns of gravitational influence that will persist for billions of years after the merger is complete. The resulting galaxy will occupy a different position within the cosmic web hierarchy, with different connections to surrounding structures and different patterns of matter accretion. The energy released during the collision will propagate far beyond the merging galaxies themselves, creating gravitational waves that will carry information about the event across vast cosmic distances. These space-time ripples will eventually reach galaxy clusters hundreds of millions of light-years away, carrying the signature of our local cosmic drama to distant corners of the observable universe. But even this dramatic event represents just a small fluctuation in the larger pattern of cosmic evolution. The cosmic web itself continues to evolve, with new filaments forming as the universe expands and existing structures becoming more pronounced through gravitational amplification. Andromeda's role within this larger pattern will continue to change over cosmic time as the galaxy participates in ever larger gravitational assemblages. The accelerating expansion of the universe, driven by the mysterious force we call dark energy, adds another layer of complexity to Andromeda's cosmic context. As space itself expands at an ever-increasing rate, the cosmic web is being stretched and attenuated, eventually breaking the connections between distant galaxy groups and clusters. In the far future, this cosmic acceleration will isolate the local group containing Andromeda and the Milky Way from the rest of the observable universe. The merged galaxy that results from their collision will find itself alone in an apparently empty cosmos, with no visible evidence of the vast cosmic web that once connected it to billions of other galaxies. This cosmic isolation will fundamentally change the nature of the galaxy's environment and evolution. Without the continued accretion of fresh material from cosmic web filaments, star formation will eventually cease as the galaxy exhausts its supply of gas. The stellar populations will age and fade, gradually transforming the merged system into a collection of ancient, low-mass stars surrounded by the cooling remnants of stellar evolution. The timescales involved in this cosmic aging process are so vast that they challenge our ability to comprehend them meaningfully. Trillions of years will pass before the last red dwarf stars exhaust their nuclear fuel and fade to darkness. During this unimaginably long twilight period, the galaxy will continue to exist as a gravitational structure, but it will be a fossil of its former self, a relic of an epoch when the universe was young and filled with the energy of ongoing cosmic evolution. Yet even in this distant future, Andromeda's gravitational legacy will persist. The dark matter halo that currently supports the galaxy's structure will continue to exist long after all the stars have died, maintaining the gravitational architecture that once held together one of the most magnificent structures in the cosmic web. This invisible monument will serve as a permanent marker of galactic evolution, a gravitational fossil that preserves information about the galaxy's properties and history across cosmic eternities. The black holes that form from stellar evolution will also persist as permanent residents of this future fossil galaxy. These compact remnants will continue to orbit within the dark matter halo, occasionally interacting with each other through gravitational encounters that can eject some black holes from the system entirely, while sending others spiraling toward the central, supermassive black hole. Eventually, even the central black hole may evaporate through Hawking radiation, though this process would take so long that the number of years required exceeds the number of atoms in the current observable universe. The final fate of matter itself remains uncertain, as we don't yet understand whether protons are stable over such extreme timescales, or whether they too will eventually decay into lighter particles. These speculations about Andromeda's ultimate fate remind us that the galaxy's story is far from over. The structure we observe tonight represents just one chapter in a cosmic narrative that will continue for periods of time so long that they dwarf the current age of the universe by factors that are difficult to express in any meaningful way. But perhaps the most remarkable aspect of contemplating Andromeda's true size is the realization that we are witnessing this cosmic giant during a very special epoch in its evolution. The universe is currently old enough for complex galactic structures to have formed, but young enough for vigorous star formation to continue throughout most galactic systems. We live during a time when galaxies like Andromeda are at their peak luminosity and structural complexity, supported by ongoing star formation and enriched by billions of years of stellar nucleosynthesis. In cosmic terms, we are observing Andromeda during its prime, when it shines with the accumulated light of 1 trillion stars and continues to grow through accretion and merger processes. This temporal perspective adds profound meaning to our observations of Andromeda's vast scale and complexity. We are not just studying a distant object, but witnessing a specific moment in cosmic evolution when structures like galaxies represent the most organized and complex systems that have emerged from the initial simplicity of the early universe. The elements that compose our own bodies were manufactured in stellar furnaces, not unlike those burning in Andromeda today. The gravitational processes that shape the galaxy's structure operate according to the same physical laws that govern planetary motion in our solar system. The electromagnetic radiation reaching us from Andromeda's stars follows the same principles that make our sun shine and warm our planet. In this sense, studying Andromeda's true size becomes an exercise in understanding our own cosmic heritage and context. We are made of star stuff, as Carl Sagan famously observed, and Andromeda represents one of the great stellar foundries where elements like those that compose our bodies have been manufactured over cosmic time. The galaxy's billion-year cycles of stellar birth, stellar death, and chemical enrichment created the cosmic environment that eventually made life possible on planets like Earth. The heavy elements dispersed by Andromeda's supernovas may have contributed to the chemical enrichment of the intergalactic medium, potentially influencing the formation of subsequent generations of galaxies throughout the cosmic web. As you continue to contemplate these impossible scales, remember that every aspect of Andromeda's size and complexity that we've explored tonight represents just a small fraction of what remains to be discovered about this cosmic neighbor. Each new generation of telescopes reveals additional layers of structure and unexpected phenomena that challenge our understanding of how galaxies form and evolve. The James Webb Space Telescope is already providing unprecedented views of star formation regions within Andromeda, revealing details about stellar nurseries that were invisible to previous generations of instruments. Future space-based observatories will probe even deeper into the galaxy's structure, potentially discovering new populations of stars, previously unknown satellite galaxies, and exotic objects that we can't yet imagine. Gravitational wave detectors may eventually become sensitive enough to observe the mergers of stellar mass black holes within Andromeda, providing new insights into stellar evolution and the dynamics of dense stellar environments. These observations would add another dimension to our understanding of the galaxy's size, by revealing processes that occur on much smaller scales, but contribute to the overall evolution of the galactic system. Advanced computer simulations are also revealing new aspects of galactic evolution that help us understand how structures like Andromeda can maintain their coherent organization over billions of years. These simulations show that galaxy formation and evolution involve complex feedback processes between different physical scales, from the quantum mechanics governing stellar nucleosynthesis to the large-scale gravitational dynamics of dark matter halos. The story of Andromeda's size ultimately becomes a meditation on the nature of cosmic architecture itself. How does the universe organize matter and energy into such magnificent structures? What physical principles allow galaxies to maintain their complex patterns over cosmic time? How do the smallest scales of physics connect to the largest scales of cosmological structure? These questions remind us that Andromeda's size cannot be fully appreciated without understanding its place within the broader cosmic hierarchy. The galaxy represents a crucial link between stellar-scale physics and cosmological-scale structure formation, a laboratory where we can study how the fundamental forces of nature work together to create complexity and beauty on cosmic scales. Tonight, as you rest under the same sky that has witnessed Andromeda's entire evolutionary history, remember that you are part of this same cosmic story. The atoms in your body, the planet beneath your feet, and the star that warms our world all participate in the same cosmic dance that gave birth to Andromeda and continues to shape its evolution across the vast expanses of space and time. The true size of Andromeda encompasses all of these connections, all of these scales, all of these mysteries that connect the cosmic past to the cosmic future. It is simultaneously a concrete physical object that we can measure and study, and a symbol of the profound questions that continue to drive our exploration of the universe and our search for understanding about our place within the cosmic web of existence. As we reach the culmination of our cosmic journey, we encounter perhaps the most mind-bending realization of all. The Andromeda galaxy that has captured our imagination tonight exists not just as a single entity, but as a constantly shifting, breathing, evolving organism that defies every attempt to pin down its exact boundaries or final dimensions. Consider this profound truth. While we've been exploring Andromeda's size through words and wonder, the galaxy itself has continued its relentless motion through space and time. In the minutes you've spent contemplating its trillion stars, Andromeda has traveled thousands of miles closer to our own galaxy. New stars have ignited in its spiral arms. Others have exhaled their final breaths in spectacular stellar death throes. The galaxy you imagined at the beginning of our journey is already subtly different from the one existing now. This temporal fluidity reveals something extraordinary about cosmic scale. Andromeda doesn't simply occupy space like a static monument. It flows through space-time like a vast river of stars and dark matter, carrying with it the accumulated history of 13 billion years, while simultaneously writing new chapters of cosmic evolution with each passing moment. The gravitational choreography governing this cosmic dance operates on scales that transform our understanding of what it means for something to be large. Every star in Andromeda influences every other star through gravitational forces that propagate at the speed of light. Changes in the galaxy's mass distribution create ripples in space-time that spread outward like cosmic tsunamis, carrying information about galactic evolution across vast distances. These gravitational waves, too subtle for our current instruments to detect from such distances, represent another dimension of Andromeda's true size. The galaxy doesn't just occupy the space we can observe with our telescopes. It projects its gravitational influence throughout the surrounding cosmic web, participating in a vast network of invisible forces that connect every massive object in the observable universe. The magnetic field lines threading through Andromeda create yet another invisible architecture that extends the galaxy's functional size far beyond its stellar boundaries. These cosmic magnetic highways guide the flow of charged particles across distances spanning hundreds of thousands of light years, creating connections between different regions of the galaxy that operate on timescales longer than the entire history of complex life on Earth. When solar wind particles from Andromeda's trillion stars interact with these magnetic fields, they create a complex electromagnetic symphony that plays out across the entire galactic volume. This cosmic music operates at frequencies far below human hearing, with wavelengths measured in light years rather than meters, creating harmonics that resonate through the galaxy's structure for millions of years. The chemical legacy of Andromeda's stellar evolution extends even beyond these magnetic boundaries through the process of galactic wind dispersal. The most massive stars in the galaxy's spiral arms produce stellar winds so powerful they can escape the galaxy's gravitational well entirely, carrying the products of stellar nucleosynthesis into the intergalactic medium, where they may eventually seed the formation of new galactic systems. This means that Andromeda's influence on cosmic chemical evolution extends across millions of light-years, enriching vast regions of space with the heavy elements necessary for rocky planet formation and complex chemistry. In this sense, the galaxy serves as a cosmic foundry whose products reach far beyond its visible boundaries, contributing to the chemical evolution of the entire local universe. The streams of disrupted satellite galaxies that flow through Andromeda's halo, like cosmic rivers, carry their own stories of scale and transformation. Each stream represents a complete galactic ecosystem that once harbored its own populations of stars, planets, and potentially even life-bearing worlds. Now dispersed across hundreds of thousands of light-years, these stellar streams create a kind of galactic archaeology that preserves information about cosmic evolution across billions of years. Some of these streams contain stellar populations so old they formed when the universe was less than 1 billion years old, making them among the most ancient stellar systems known to exist. Their chemical compositions provide windows into the early epochs of cosmic history, when the first galaxies were condensing from the primordial cosmic web and beginning their long journey toward the complex structures we observe today. The dark matter scaffolding that supports all of these visible phenomena extends Andromeda's gravitational influence into realms we can barely imagine. Computer simulations suggest that this invisible architecture may contain substructures and density variations that create a complex gravitational landscape spanning several million light-years. Within this landscape, streams of dark matter flow along cosmic highways that connect Andromeda to distant galaxy clusters across hundreds of millions of light-years. These dark matter currents carry no visible light, emit no detectable radiation, yet they may transport more mass than all the visible galaxies in the local universe combined. They represent a hidden circulatory system that connects cosmic structures across vast distances, creating a network of gravitational influence that shapes the evolution of entire regions of space-time. The approaching collision between Andromeda and our own Milky Way takes on even more profound significance when viewed against this backdrop of cosmic connectivity. The merger that awaits us represents not just the meeting of two isolated galactic systems, but the convergence of vast streams of dark matter, magnetic fields, and stellar populations that have been flowing toward each other through the cosmic web for billions of years. When these systems finally merge, they will create gravitational disturbances that propagate throughout the local cosmic web, redirecting matter flows and creating new patterns of structure formation that will influence cosmic evolution for billions of years to come. The collision will serve as a kind of cosmic watershed, fundamentally altering the gravitational landscape of our local universe. The energy released during this merger will briefly transform the local group of galaxies into one of the most luminous objects in the observable universe. The gravitational waves generated by the collision will carry information about this cosmic event across distances so vast that they may still be detectable by future civilizations living in galaxy clusters billions of light years away. But even this dramatic transformation represents just one note in the vast symphony of cosmic evolution that has been playing since the universe began. The structures we observe today, from the smallest asteroids to the largest galaxy clusters, all participate in this ongoing composition, each contributing its own voice to the eternal music of gravitational attraction and cosmic expansion. So as you drift into sleep tonight, carrying with you these impossible scales and profound mysteries, remember that the faint smudge of light we call Andromeda represents something far more magnificent than numbers could ever capture. It's a trillion-star symphony of cosmic evolution, a gravitational cathedral spanning millions of light years, a temporal bridge connecting us to the deep past and distant future of our universe. In understanding how truly vast Andromeda is, we glimpse not just the scale of our cosmic neighbor, but the infinite wonder of existence itself. Sweet dreams, fellow traveler in this magnificent cosmic story.